Hi, on this video for Financial Math for Actuarial Exam 2, we'll be taking a look at a starred problem 4.1.23 in Broverman's book. Starred problem is a little extra hard, or in this case actually just a little extra theoretical. We'll be finding an unknown quantity in something called Makeham's formula for a bond price. I haven't mentioned what Makeham's formula is to this point. I'm going to take the opportunity provided by this problem to talk about it. So here is the problem. A bond issue carries quarterly coupons, not semi-annual, but quarterly, of 2% of the face amount. So for example, if the face amount is 1,000, then 2% of that is 20. That would be your coupon amount every quarter. An investor uses something called Makeham's formula, which I'll talk about in a few minutes, to evaluate the whole outstanding issue in order to yield an effective annual rate of 13%. The goal is to find the value of H that is used in this formula for the price, P equals K plus H times, in parentheses, C minus K. P is the price, which is the present value of all the future payments. C is the redemption amount. So far in looking at this formula, you don't know what K or H are. We have not seen those before. What will those quantities represent? Let's start from scratch. We'll draw our timeline and think about the formula for the price and possibly rewriting it in different ways to make it look like this. So here we have the timeline. These would be the periods, which in this case would be quarters, but in general could be semi-annual, half years, or even annual coupons. If F is the face amount and R is the coupon rate, then F times R is the coupon amount that you get at the end of each period, up through and including the last period when you also get your redemption amount, C. So what is the price? P. The price is going to be the present value of all these amounts. Back at time 0, you've got this annuity immediate for the coupons. F times R. Multiply it by ANJ for its present value, where N is the number of periods here, and J would be the effective periodic interest rate. That would be quarterly. In this case, it's not 0.13. We'll have to figure out what J is. Plus the present value of the redemption amount, C. We need to bring that back to time 0, so we multiply by the discount factor, V sub J to the N power. V sub J would be 1 over 1 plus J. Okay, that's the way we've typically thought about the bond prices. Now we're going to rewrite this by first of all making an assumption. I'm going to assume in this video, as we usually do, that C equals F, the redemption amount equals the face value, as it usually does. Very soon, maybe even the next video, we'll consider situations where the redemption amount is not the same as the face value. So that's one assumption I'm going to make. I'm also going to let K equal the present value of the redemption amount, C times Vj to the N, or if you prefer, F times Vj to the N for this example based on this assumption. Okay, so if we make those, that assumption and that definition, what happens to this pricing formula? Let me, first of all, just change the order. I'll put this first, and I'll just go ahead and call it K. So K represents that amount right there. And let me go ahead and replace that F with a C. You don't see any F's in this formula here, so I'm going to go ahead and make that replacement. And I've got times R times A and J, which would be 1 minus Vj to the N divided by J. Let's see. It's going to turn out that this H is going to be R over J. Let me rewrite this as K plus R over J. Let me multiply the C through the parentheses to get C times 1 minus C times V to the N. And there we go, that's K again. And if I let H equal R over J, then I get the final formula that you see right here. P is K plus H times C minus K. Okay, so as far as solving the problem goes, all we need to do is find R over J. Find the value of H, which is going to be R over J in this formula. After I go ahead and find that, then I'll talk a little bit more about the formula and how it's useful. All right, so how do we find it? We just find R over J. We already know R is 0.02. That's the quarterly coupon rate. J is related to 13%, but it does not equal 0.13. J, if you think about it, is going to be 1.13 to the 1/4 power minus 1. It's going to be an effective quarterly rate for the yield, the effective quarterly yield. So let's find that. 1.13 raised to the 0.25 power minus 1. J is approximately 0.031. I can plug that in here. So let me go ahead and take its reciprocal and multiply it times 0.02. The answer to the question is about 0.6446. H is approximately 0.6446 as the answer to the question. This is an approximately equal to symbol. That answers the question. Find the value of H in this formula. But what does the formula mean? What is it good for? Let's end the video by focusing on the formula. And let me go ahead and not have the H in there, but instead have the R over J in there, like this. Okay? So certainly this formula would be useful if you happen to know the redemption amount, C, when it does equal the face value, say. If you happen to know the periodic coupon rate and periodic yield rate. And if you happen to know K, the present value of that coupon amount, certainly you can plug the numbers in and find the price. Probably a more important use is just to think about it a little bit and think about what happens in relating P and C when you have different relationships between R and J. If R over J happens to be bigger than 1, meaning the coupon rate, the effective periodic coupon rate is bigger than the effective yield rate, what will that imply? That implies that P, which is this, will be greater than K plus C minus K. It'll be greater than C. The price at time 0 is going to be greater than the redemption amount when the coupon rate is greater than the yield rate. This thing here is equivalent to R being bigger than J. On the other side, the flip side, if R is less than J, meaning R over J is less than 1, that will imply that P is less than K plus C minus K, because this thing here will be less than 1. It'll be less than C. The price will be less than the redemption amount. And of course, then if R equals J, that'll be equivalent to P equaling C. The price at time 0 will be equal to the redemption amount at time M. Okay, so that's perhaps the most important use of it, to see those relationships. But you can use it with particular numbers, and you can solve problems like this here.